Hey everyone, have you ever grabbed a metal can of soda straight from the fridge and been like, whoa, that's cold? Like way colder than a cardboard juice carton, even if they've been in there the same amount of time.
It's a great question, and it's all because today we're going on a deep dive into heat energy.
Yeah, we'll be figuring out how it moves, what it does, and some of the cool ways we see it in action every day.
We'll uncover secrets like how huge buildings with those giant glass domes like the Changi Airport can stay cool even when it's super hot outside,
And we'll even tackle things like why hot air balloons can float.
and why those polar ice caps are unfortunately melting.
But before we get ahead of ourselves, we got to start with the basics.
You got it.
What exactly is temperature?
Well, it's more than just hot and cold, you know?
Yeah, like how do we actually measure it, and what does it even mean?
Right, well, temperature is really about how much those tiny little particles inside things are moving and grooving.
Okay, so those tiny particles are called atoms and molecules, right?
Exactly, and they're always jiggling and vibrating.
So the faster they jiggle, the hotter something is.
Exactly, and here's the thing. Heat energy never stays still.
Mm-hmm.
It's always moving from hotter objects to colder ones.
Like it's trying to share the heat love.
Yeah, you could say that. It's always trying to even things out.
Like a game of hot potato?
Yeah, remember that cold soda can you were talking about?
Uh-huh.
The heat from your hand basically zipped right into the metal because metal is what we call a great conductor of heat.
It's like a super speedway for heat to travel on.
You got it. Materials like cardboard are kind of like those bumpy dirt roads for heat. They slow it way down.
That's why the can feels colder, even though they're technically the same temperature.
Precisely.
You know, this makes me think about those gaps you see in railway tracks.
Ah, yeah, good one.
Why are they there?
It all comes down to how heat messes with the size of things you see when things heat up.
They get bigger.
They do those tiny particles. They need more space to jiggle around so the whole thing expands.
And when they cool down...
The opposite happens. They contract. They shrink.
So those gaps in the railway tracks are like breathing room.
Yeah, exactly. They give the metal space to expand on those scorching hot days because if they didn't have those gaps, they could buckle under pressure, and you wouldn't want to be on a train riding on those tracks.
No, definitely not a smooth ride.
Not at all.
It's pretty amazing how these tiny particles can affect big things like train tracks.
Oh, absolutely.
And it's not just solids that are affected, right? Liquids expand and contract too.
You're absolutely right. Think about when you're struggling to open a drawer lid
Oh, yeah.
and you run it under hot water.
Classic trick.
The metal lid, it expands more than the glass jar, making it easier to twist off.
It's like giving those metal particles a boost of energy.
Exactly. Now let's shift gears a bit and talk about how heat actually gets around. It's got three main ways of doing it.
3 moves.
Yeah, conduction, convection, and radiation.
Okay, so break it down for us.
Right, so first up, conduction, it's all about direct contact.
Okay, so like when a hot object touches a colder one.
Right, imagine you and your friends are passing a secret message down a line. Each person whispers it to the next.
Sharing secrets.
Exactly. Well, conduction is similar to that, but on a super tiny level.
So instead of secrets, it's heat energy being passed.
You got it. When a hot object touches a colder one, the fast-moving particles in the hot object bump into the slower ones in the cold object, and those collisions pass the energy along.
So it's like a chain reaction of tiny bumps.
Precisely. And remember, metals are like those superhighways for heat, making them great conductors.
All right, conduction check. Got it. What about convection?
Convection is all about currents. It's like a lava lamp. Those blobs of wax rising and falling, that's convection in action.
Oh, I love those things. So how do those currents actually work?
Well, when you heat up a fluid like a liquid or a gas, the warmer part becomes less dense and it rises.
It wants to float up.
Exactly. And the cooler part, it's denser, so it sinks. And this creates this continuous cycle of rising and falling fluid carrying heat energy along with it.
So it's like a constant swirling party of hot and cold.
You could say that, and you see these convection currents everywhere. Like, think about a pot of water heating on the stove.
Okay, yeah.
The water at the bottom heats up. First, it gets all light and bubbly and rises up. Then the cooler water from the top sinks down to replace it, and the cycle continues.
So like a never-ending dance of water molecules.
That's a great way to put it. And it's not just water that does this. Air moves in convection currents, too.
This is making me think about those breezy days at the beach.
Yes, those refreshing sea breezes. That's convection at work.
But how does the ocean send us those cool breezes?
Well, during the day, the land heats up faster than the sea, so the air above the land warms up, gets less dense and rises, and then cooler air from over the sea rushes in to replace it, and voila, a sea breeze is born.
It's like the land is a giant heater and the ocean is a giant AC unit.
That's a great way to think about it. And that brings us to our last heat transfer superstar radiation.
This is the one that's like sunlight, right?
You got it. Radiation is heat transfer through electromagnetic waves. It doesn't need any matter to carry it, so it can even travel through the vacuum of space.
So like how the sun's heat reaches us here on Earth.
Exactly. The warmth you feel on your face from the sun, that's radiation traveling millions of miles to get to you.
That's mind-blowing. So it's like the sun is a giant space heater.
You could say that, and here's another cool thing about radiation.
What's that?
Every object actually radiates some amount of heat energy depending on its temperature.
Though even we radiate heat.
We do. It's just that some things radiate more heat than others. And another interesting thing is that different colors can actually absorb and emit heat differently.
Okay, so like how dark-colored cars get way hotter in the sun than light-colored cars.
Exactly. That's because dark colors absorb more of that radiant energy while lighter colors reflect it back.
So it's like dark colors are heat magnets.
That's a great way to put it. Now, how about we see how these 3 heat transfer moves work together in the real world?
I'm ready for some real-world action.
All right, let's head to the Arctic and talk about igloos, those incredible shelters built by the Inuit people.
Igloos? Wait, how can something made of ice keep people warm?
That's what's so cool about them. They're a perfect blend of all 3 types of heat transfer working together to keep people cozy even in freezing temperatures.
I'm intrigued.
So first off, those thick walls of packed snow and ice act as an insulator, slowing down heat loss through conduction.
So it's like a giant cooler, but instead of keeping things cold, it keeps them warm.
Exactly. The small entrance and the limited ventilation help to minimize heat loss through convection.
So it's like trapping a pocket of warm air inside.
Right, and to reduce heat loss through conduction even further, the Inuit people would build a raised platform inside the igloo and cover it with furs and skins, creating multiple layers of insulation.
It's like building a cozy nest within a frozen dome.
Exactly. And to generate heat, they would burn seal fat for heat and light, and that heat would be transferred to the people inside, mainly through radiation.
So they were really masters of using heat transfer to their advantage.
Absolutely. It's a brilliant example of how understanding these basic principles of heat can make all the difference.
This whole deep dive has been so eye-opening. I'm starting to see heat transfer everywhere, from the way my soup cools down to how the sun warms my face.
It really is a fundamental part of our world, and there's so much more to explore. We've just scratched the surface.
Can't wait to dive in deeper. We'll be back soon to uncover even more amazing facts about heat energy.
Welcome back. Before the break, we were talking about those awesome igloos and how they use all 3 types of heat transfer to stay warm in the Arctic.
I'm still thinking about those igloos. It's so cool how the Inuit people figured out how to work with nature like that.
It shows you how understanding a little bit of science can make a big difference.
Yeah, totally. And speaking of science, let's dive a little deeper into some of the things that can speed up or slow down how quickly heat travels.
Sounds good.
We already talked about how different materials conduct heat at different speeds, like how metal is like a heat superhighway and wood is more like a bumpy back road. But what else affects how fast heat travels?
Well, when it comes to conduction, the amount of heat that gets transferred depends not only on the type of material, but also on the difference in temperature between the 2 objects and how much surface area is actually touching.
Okay, so the bigger the temperature difference, the faster the heat flows.
Exactly. It's all about how much energy those particles have to share.
So like touching a hot stove is going to be a lot worse than touching a lukewarm cup of tea.
Exactly. And the more surface area that's in contact, the more heat can be transferred.
Okay. I'm trying to picture this.
Imagine you're trying to cool down a hot pot. If you spread it out on the countertop, it'll cool down faster than if you leave it all bunched up because more of its surface is touching that cool counter.
Oh, that makes sense. More contact means more chances for those heat particles to escape.
So for conduction, it's all about the material, the temperature difference, and the surface area.
Got it. Conduction check.
For
What about convection? Does the speed of those currents matter?
Absolutely. The rate of convection is affected by the type of fluid, the temperature difference, and how fast the fluid is moving.
Okay, so a strong wind is going to create faster convection currents than a gentle breeze.
Exactly. It's like how a pot of water boils much faster when you crank up the heat on the stove.
Yeah, those bubbles are like convection currents in action.
Exactly. And the type of fluid matters too. Water, for instance, is a better conductor of heat than air. So those convection currents in water are usually stronger than those in air.
Okay, so we've got the type of fluid, the temperature difference, and the speed of the flow. That leaves us with radiation. What affects how much heat travels through those energy waves?
With radiation, the key factors are the temperature of the object that's giving off the radiation, how much surface area it has, and what kind of surface it has, its texture, and its color.
So like we talked about earlier, how dark colors absorb more heat radiation than light colors. Does that mean they also give off more heat radiation?
Exactly. A black object will radiate heat energy faster than a white object at the same temperature.
Interesting.
And a rough surface will radiate heat more quickly than a smooth one.
It's like those dark colors are soaking up all the sun's energy and then blasting it back out.
That's a great way to put it. And just like with conduction and convection, the larger the surface area, the more heat can be radiated.
This is making me think about those electronic devices with all those fins sticking out.
Yes, exactly. Those are called heat sinks, and those fins increase the surface area, allowing the device to get rid of heat more efficiently.
So it doesn't overheat.
Exactly. It's pretty amazing how we figured out how to manage heat transfer to make things work better.
Totally. It's like we've learned to speak the language of heat.
We have, and now that we've got a good grasp on the basics, let's look at some real-world examples of heat transfer in action. We've already touched on a couple like igloos in green buildings, but there are so many more.
Ready for more.
Well, one of the most common and delicious applications of heat transfer is in cooking.
Oh, yeah.
From frying pans to ovens to kettles, we use heat transfer every day to turn raw ingredients into yummy meals.
I never really thought about it that way, but you're right.
A frying pan's metal base conducts heat quickly from the stovetop to the food, and those convection currents in a pot of boiling water help to distribute the heat evenly, so everything cooks just right.
It's like a perfectly choreographed dance of heat.
And ovens are masters of combining all three types of heat transfer. The heating elements radiate heat, and then convection currents spread that heat throughout the oven, and the food itself absorbs heat through both radiation and conduction.
It's like a team effort, convection and radiation all working together to make our food delicious.
Exactly. And we also use heat transfer principles to keep things warm or cold. Woolen clothing, for instance, keeps us warm by trapping air, which is a poor conductor of heat in its fibers.
So it's like wearing your own personal igloo.
That's a great way to put it. And double-glazed windows use a similar principle to help keep heat inside buildings.
Yeah.
The layer of air trapped between the two panes of glass acts as insulation, slowing down the transfer of heat through conduction.
It's like a built-in heat shield for our homes.
Exactly. And then we have cooling fins in things like car radiators and refrigerators. Those fins increase the surface area for heat radiation, helping to get rid of heat quickly and keep things cool.
It's amazing how we've learned to manipulate heat transfer in so many ways.
It is one of the best examples of this is the vacuum flask, also known as a thermos.
Oh, yeah, those things are amazing. They can keep hot drinks hot for hours and cold drinks cold all day long.
Exactly. And it's all thanks to clever design that minimizes heat transfer through all three mechanisms, convection and radiation.
Okay, break it down for us. How does a vacuum flask manage to be such a heat-stopping champion?
First, it has a double-walled construction with a vacuum or empty space between the walls. Since there's no air in that vacuum, there's no conduction or convection happening there.
So it's like creating a heat-free zone.
Exactly. And to further minimize heat transfer, the inner walls of the flask are usually silvered. This helps to reflect radiation, bouncing that heat energy right back where it came from. And finally, the flask has a tight-fitting lid to prevent any heat from escaping through convection.
It's like a maximum security prison for heat energy.
That's one way to put it, all those layers working together to keep the temperature inside stable.
It's brilliant.
It is, and it's a great example of how understanding the principles of heat transfer allows us to design incredibly effective solutions.
This has been such a fascinating journey into the world of heat transfer. I'm starting to see it everywhere, from the way my soup cools down to how the sun warms my face.
It's truly remarkable how something so fundamental to our existence can be so complex and fascinating.
And there's still so much more to explore. We've only just scratched the surface of this incredible subject.
I can't wait to dive even deeper. We'll be back after a quick break to continue our exploration of the amazing world of heat energy.
Welcome back to the deep dive.
Yeah.
We were just talking about those awesome vacuum flasks before the break. You know, those thermoses that can keep things hot or cold for hours?
They really are a marvel of engineering, aren't they?
Yeah.
And they're a great example of how we can use our knowledge of heat transfer to design some pretty amazing things.
Totally. It's like we've become masters of controlling heat.
Exactly. And speaking of mastering heat flow, it reminds me of those igloos we were talking about earlier. They're such a fascinating example of heat transfer in action.
Oh, yeah, those igloos.
Yeah.
I'm still kind of blown away by the fact that something made of ice can actually keep people warm.
I know it seems counterintuitive, right? But the Inuit people have been building and living in igloos for thousands of years. They've learned how to work with nature and use their understanding of heat transfer to survive in some of the harshest conditions on Earth.
So how do they do it? Remind us how those igloos actually work.
Well, it all starts with those thick walls of packed snow and ice.
Okay.
They act as an insulator, slowing down the transfer of heat from the warm interior of the igloo to the cold outside air. That's conduction at work, or rather the lack of it.
So it's like having a giant blanket of snow wrapped around you.
Exactly. And then there's the shape of the igloo. That domed shape and the small entrance help to minimize heat loss through convection. You see, the warm air inside the igloo tends to stay trapped up near the top, while the colder air sinks to the bottom. And because there aren't any big openings or drafts, those convection currents are kept to a minimum.
So it's like creating a little pocket of warmth inside.
Right. And to make things even cozier, the Inuit people would often build a raised platform inside the igloo and cover it with furs and skins.
Oh, wow. So they were adding extra layers of insulation?
Exactly. They were essentially creating a warm and cozy nest within that frozen dome. And of course, they also needed a way to generate heat.
Makes sense. How do they do that?
They would burn seal fat for heat and light, and that heat would be transferred to the people inside mainly through radiation.
Wow. So they were really harnessing all three types of heat transfer, conduction, convection, and radiation to stay warm and comfortable.
They were. It's a remarkable example of how understanding basic science can have a huge impact on our lives.
It makes you realize that science is all around us, not just in textbooks or labs.
Absolutely. It's in the way we cook our food, the way we stay warm, the way we design our homes. It's woven into the fabric of our everyday lives.
This whole deep dive has been such an eye-opener. I feel like I'm seeing heat transfer everywhere now.
I'm glad to hear that. And remember, the principles we've talked about today aren't just about igloos or thermoses. They apply to so many things.
Totally, like how we were talking about dark colors absorbing more heat from the sun than light colors. So if I'm going to be out on a hot, sunny day, I should wear light-colored clothes to stay cooler, right?
Exactly. And if you're out on a cold day, wearing darker colors might help you absorb a little bit of extra heat from the sun.
So it's like I can choose my own personal climate control system based on the color of my clothes.
You got it. It's all about understanding how heat works and using that knowledge to your advantage.
Well, I think it's safe to say that we've all learned a lot about heat energy today.
We have. It's been a fascinating journey into the world of heat transfer.
It has. And I think it's amazing how something so fundamental to our existence can be so complex and intriguing.
I agree. And the more we learn about heat, the more we can appreciate the incredible beauty and complexity of the world around us.
That's a great point. Well, thanks for joining us on this deep dive into the world of heat energy. It's been a real pleasure.
The pleasure was all mine. And to all our listeners out there, keep exploring, keep asking questions, and keep discovering the wonders of science.
That's great advice. We'll see you next time on the deep dive.